Hi. So, in the context of post-training LLMs, we've spoken about SFT, supervised fine-tuning. And what we saw was, well, we were still just, minimizing the cross entropy error based on the mistakes in the output tokens by masking the bit where we had the prompt. And all we do is we just change the data set, right? Instead of just training on the next word from, let's say, the internet, we now curate a very specific data set with that context, prompt and answer, triplets. So that is all that there is in the SFT step. And now we want to talk about RL based fine tuning. So why do we need this RL? Why do we need to move to reinforcement learning based fine tuning? And well, the reason is that SFT, supervised fine tuning, treats all samples equally, and reinforcement learning weighs them by quality. And essentially, SFT is what kind of tells the model to memorize something as the right answer, but RL instead gives it criterions and then says, okay, these are my criteria, go and practice and improve on those. So how do we do that? Well, before we do that, let me quickly introduce some notation. It's simple. It'll just help us, get into the math of it slightly easier. So, let's always run with this sentence. The quick brown fox jumps over the lazy dog. And we will name all these words as tokens. Token 1, token 2, token 3, token 4, and all the way to token T. Okay, and the token at position T, the answer that we want to predict, right? AT is what we want to predict, and this is also known as token T. And this ST is essentially what we have, all previous token. You can also call it the context. In the realm of reinforcement learning, we also call it state, right? So this is the state, ST, and then we have pi. It's essentially the probability model assigning the token at a given context ST. So basically what we want to predict is AT given ST, and pi is essentially the function. In reinforcement learning, we sometimes call it policy. It's nothing but actually the LLM itself, but this is just notation that I want you to know. And what we want the LLM to do is we want it to maximize pi of, let's say, A of t given S of t. So if my current A of t is jumps, suppose it has predicted till here and we want to predict this, then what we are saying is, okay, what is the probability of jumps given it has already predicted the quick brown fox? It can also be written in a concise manner by saying pi of A5 given S5, right? So S5 essentially is everything until then, and then A5 is essentially that particular output that we're interested in. So compact notation so that we can express training objectives precisely. And now what we want to do is we want to, so one thing which is interesting is to understand, that we are essentially minimizing the same loss, essentially the next token loss, right? And what we want to say is we want to learn the whole sequence. So we want to know the probability of the first token. There is no ST before this because this is the first token. Then we want to, and why are we multiplying these together? Because we want to maximize the whole thing. Another interesting thing to note is that probably, RL people were more optimistic. So they spoke about rewards and things which were positive. And I think machine learning people were more pessimistic. So they spoke about losses, and minimizing it. So we maximize a reward and we minimize a loss. But here we're talking about rewards. And what we are saying is, okay, we want to maximize this probability. We want to maximize the probability of A1. Then we want to maximize the probability of A2 given S2. Then we want to maximize the probability of A3 given S3, and so on, all the way to, probability of AT given ST. So what we then do is we just take a log, right? Because we can then convert, let's say, these multiplications, the multiplication of all these probabilities into, let's say, a summation, right? So if you just take a log of this, you can write this then as a sum of logs, right? So you can write this as a sum of t equal to 1 from here all the way to capital T of log of pi of at given st. And then we want to say, because we want to minimize the loss, because we want to bring it into the framework of large language models, we just put a negative outside this, and this is essentially your cross entropy loss, right? Negative of the correct class, right? And then you sum it up over all the tokens, and then you get the, let's say, loss for that entire sequence. And this is the same cross entropy loss, but with this kind of a notation. And now we want to talk about a very old, let's say, paper, reinforce, right? So reinforce was one of the very first papers to kind of talk about reinforcement learning. And let's talk about first the basic version of it, right? And in the basic version, what are they saying? They're saying, okay, if reward of text I is essentially the reward for the full response, for the full sequence, and let's say this is the probability of every token, how likely the model thinks this token is, then what we do is we multiply this token loss along with the reward for that entire sequence. How we get this reward is a topic for the next few slides, but let's say magically we can get this reward from somewhere, right? So all we are saying is, okay, not all sentences are equal. Some sentences are like more than others. For example, if let's say I write something versus somebody who's much better at writing, at English, writes something, I want to give that more score than what I would write. Yeah, and then what somebody else would write, I want to give it maybe less score. And this is where the reward comes from. And this reward, interestingly, may not always be differentiable, right? It can just be a scalar that a human assigns or so on. But all I want you to remember is that this is essentially weighted cross entropy. So we have two loops here, one over the tokens itself and then one over the sequences. So I is over the sequence and T is over the tokens. So every sequence, every sentence may have a different reward. It's magical right now, it comes from somewhere, we'll talk about in a second where it comes from, but just remember that we are kind of talking about this scaled cross entropy loss, right? And we divide it by S to normalize it, right? Because this is basically the batch size and we want to make sure that we have the same loss for everything. Now the problem with raw reinforce is that let's say our output, our scores are always between 91 to 100, right? 90 to 100, because that is how we asked people to score it, or that is how something else outputted those rewards to be. And then the problem is that let's say we have a good response which is 98, because then sometimes you say, okay, what is your pain level between 1 to 10, 1 being let's say very little and or 1 being very high and 10 being very low. What is your happiness between 1 and 10, 1 being very low and 10 being very high? So 1 would sometimes be negative, right? If I say, okay, I think I'm 2 happy or 3 happy, right? So but here if it's let's say between 91 and 100, what happens is that it still reinforces, the model still thinks that okay, this is a great output, and it gives it a very positive reward, a very positive scaling factor. So the solution is simple. We want to introduce a baseline. We simply want to basically say bring the origin to about say 95, right? So we have this 0 here and the average of all these rewards let's say was 95. We want to say that okay, we want to just bring the average to 0. And now, so essentially you want to sum all of it up and then subtract 95 from all of it. Then what happens is we get these negatives which we want to penalize. This is my negative reward, and then we have a positive, and this positive is my positive reward. So whenever it's positive, I actually want to boost that output. I want to get more of that. I want to be more happy. I want to be less painful. And then when I want to penalize it, when I want less of that, I want to have it in the negative regime. And this is also called as the advantage function. So in notation, we write it as r minus v. V is in some sense an average. It's called the value function. R is called the reward function. Yeah. But let's look at how it actually works. So again, it's r minus v. Right? R is my reward that we've been talking about. V is this value function that I've been talking about, right? So V is essentially the average that we subtract from R to bring it at the origin. But how do we do it? Yeah. So how do we do it is really, really interesting. But let's first just formalize it. So what I'm saying, just what we discussed in the last slide, is you have, let's say, we have a reward. Right, we have a reward for that particular sequence. By the way, Williams et al. In 1992 came up with this reinforce in trial and error with a multiplier, where they have, you know, this multiplier reward, and then they also introduced this additional baseline of this value function. So what we are saying is we have the reward for the full response for that entire sequence I, r text of I. We have these individual probabilities of how likely the model thinks the current token is. We have r minus v, which we call the advantage function. How much better or worse the reward is compared to our expectation. Expectation is just a fancy word of, let's say, for mean, right? So and advantage is again an important word to remember when we talk about reinforcement learning. You can also think of this post-training LLMs as a very easy way to get into RL, right? Because you kind of get a hang of the notation, you kind of get a hang of how things work, and then you can do reinforcement learning for robotics, for all other things where there is no LLM involved. So again, if you remember the previous slide, we did not have this. So all I did was I added this V of ST, right? So the baseline expected reward given the current output, given the current sequence that I've already output, the quick brown fox, right? If I am at jumps, I still have the quick brown fox, and the value function will take this state, will take, you know, this history. And reward is something that is decided for that entire sequence. Your value function is for a particular token, and you see value function is essentially, okay, let me rub this a bit. So value function iterates over, so you know, so another thing I want you to know is, you know, whenever you see these signs, it looks complicated, but just think of in your head as for loops. And here we have an inner for loop and an outer for loop. The inner for loop is something that goes faster, so tokens, because every sequence has tokens 1 to t, and then this is over the sequence, right? So sequence I equals 1 to n, and then your reward is per sequence, but your average, your value function is at the current token. Yeah, you can think of the reward as, let's say, the future, but the value function as the present. So the average is something that keeps changing, and then the reward is, let's say, at the end of the sequence. And the simplest way to do this value function is just a running mean, right? I saw the quick brown, I just calculate the average of reward until here and then penalize based on that, right? So then I subtract this, and then this keeps changing. The quick brown fox, the quick brown fox jumps, the quick brown fox jumps over. So the value function keeps changing, but the reward remains same because the reward is for the entire sequence. And then this is nothing but our simple cross entropy loss. Did I output the correct token or not? But you must be thinking, where is this reward coming from? Where is this value function coming from, right? And these are all very, very good questions, and let's see how. So this is just to kind of concretize what we just spoke, the value function and the advantage. What is the value function? The value function is V of ST, the value of given the current states. What is the advantage? Advantage is nothing but R minus V. Yes. So for example, here is my value function 5, here is my actual reward 7.0, but then the advantage is only 2 because it's R minus V. Similarly here, if my expected value is 5, but my actual reward is 3, then it's 3 minus 5, so minus 2. I want to penalize it. I don't want to see such outputs in the future. Okay. And where does this reward come from? How do we do it in the context of LLMs? And the idea is actually very simple. So what we do is we train a reward model by a human using preference pairs, the Bradley-Terry model, right? So what we do is we say, you may have seen in Gemini, in ChatGPT, it gives us two different outputs, and then it says, okay, I like this one versus I like this one, right? So as a human, you're choosing this over this. Yeah. So this is how you collect data, and this data is categorical data, right? You can use, so this is basically a classification data. And then you say, prefer A over B is given by a sigmoid over reward of A minus reward of B. Yeah, and essentially it's 1 upon this exponential. So it's this sigma of reward A minus reward B, and this is what we want to maximize, right? So think about it, right? If I have a sequence where A is always better than B, because that is how I have arranged my data, I want my reward to be higher for where the human has said, okay, this is A is better than B always, right? That is how I've arranged my data. And then I put a sigmoid. What is the sigmoid doing? It's essentially making everything in the 0 to 1 range. My domain can be anything, it's just making my range into 0 and 1. So the reward can be anything, but then my reward A minus reward B may be some number, maybe minus 100, maybe plus 1000, but the sigmoid will squish it between 0 and 1. And this is, you can do a negative log of this, for example, to then know the loss, right? So if my reward is very high, then it will almost be 0, and if my A is very high as compared to B, then I want my loss to be very low, and I want my loss to be very high otherwise. So this is not important. What is important is what I then, so you see, this is what I was saying. So I have my reward, so reward A minus reward B, and reward A minus reward B is just nothing but the sigmoid of, let's say, reward A minus reward B, and then so negative log of this, so preference, right? So negative log of the correct class. If I say, A is the better one, then I want the negative log of this. If I say B is the correct one, I want the negative log of the other one, right? 1 minus this, for example, 1 minus sigma of RA minus RB. You can also, like I said, just change data so that RA is always high, and then it will always be negative log of RA minus RB, right? So the loss is simple. This is how we kind of train the reward model. But then what does the architecture look like? And the architecture is brilliant actually. And what we do is, okay, let me just rub this off. So what we do is, you remember our transformer model, you remember our large language model. So our large language model, what does it look like? There is a bunch of tokens that come in and it enters, let's say, our transformer block, and then the transformer block gives out these exact 3 tokens, and then we have a linear layer on this, remember, and this linear layer projects it from, say, 4192 to 50,000, right? This is the entire vocabulary. So when you train the reward model, you don't have this head, instead you have this other head which just outputs my reward. Yeah, and this can be, it's just linear layer, and now it's going from 4192 to just 1, right? Because it just outputs a scalar reward for sequence A, reward for sequence B, reward for sequence C, and so on. And then we get it to output, rewards for, let's say, 2 different sequences, and then we compute the loss based on this Bradley-Terry model. This is basically simply a sigmoid over the difference between the good and the bad response with a negative log of the correct class. right? And here in the graphic I explained just this. So you get humans to rate just the way ChatGPT gets us to rate, and then we train this reward model, and then the reward model knows how to predict a scalar, how to predict 7.2, and then it's very simple what we do, right? Then we have two models. We have a reward model. This is as big as your original LLM, except for that last linear layer, which is negligible when you compare the entire size of the whole LLM. So you have your reward model. So this is a specific model, and then you have your LLM that you're actually training. And this is one of the disadvantages that we talk about later, right? So you need to have a full big model in memory when you're fine tuning your LLM, because your LLM will output something and then you will get the reward, and then you will backpropagate the reward into that. Another thing to note is, what about the value function, right? So the value function is actually another, let's say, LLM. You can also add it as an additional head into the same model. Yeah, so you can have the same model which has the reward, and the reward takes the final this thing. So you have one reward head. You can also have a value head. And the thing to think about is that the reward is calculated at the end of the sequence, right? But this value is calculated at every time step. And initially, this is just a copy of, let's say, R. So we don't know how to train value. There is no ground truth for value. The ground truth for value, the training for value comes from every time step. So we train it as we are training the LLM, right? Because we have, let's say, the value coming out, and that should be the average reward until then, right? So initially we just copy the reward over here and we just start training. But you may think that, okay, won't the value and reward always be same, and won't R minus V always be 0? That's a good question, but the answer is no. Why? Because reward is at the end and the value. So initially when we have just copied the reward into value, and we look at, let's say, the reward of just the first token, it will be different from the final reward of that entire sequence, right? And thus R minus V will be something meaningful and not gibberish. And then we will also know the ground truth, because we know the reward until here, because our reward model is already trained. So we are then also able to train value. We are able to back propagate into value, and value has to be a differentiable function. It is a learned function, though reward need not be a differentiable function, but in case of our LLMs, yes, it is a differentiable function. Yeah, so this is all that there is in reinforcement learning with human feedback. So reinforcement learning with human feedback is a framework, and reinforce, what we just saw, is an algorithm for the learning part. So in RLHF loop, what do? We get humans to label responses, pairs of responses. We compute the reward signal. We update the model weights, right? So to compute the reward signal, you also have to train a reward model, just the way I spoke about here. And then once we have our reward and value functions, then we can use this R minus V to weigh our cross entropy loss when we train our LLM after the LLM generates a response. Yeah, so that's all that there is in RLHF.